Start the video. Welcome, welcome, welcome. I'm Lisa Blackburn. This is my YouTube channel for everything I like, science and math. And today we are talking about the atom and energy, which is Unit 3 notes. All right, so everybody's got your paper, and let me find where I put my pen and my paper. Here it is. I need to make a little note of how far we got in the other class. Ended first. I tried to write it on there. But my little board is like not being too happy. I think I freaked it out by getting too fancy. Did you notice how I colored it? I think it might have freaked it out. We might have to go back to not so fancy. All right, so write your name on it. Now, so what we're talking about is that there are elements on the periodic table that are radioactive. Their ratio of protons to neutrons is not in the stable area. We're going to talk more about that. And they just give off particles. They fall apart. Everybody follows that idea so far? Good? All right. So it turns out the elements over number, I got to draw green. Elements over 92 are all synthetic. They're man-made. They are not found in nature. So if you look at the periodic table over here, there are these and those. And if you look at this periodic table, they're white. See all these white ones? These are fake. They were made in a lab with an atom smasher. There's something called the Large Hadron Collider in Switzerland, and it's the biggest, newest, best one of these things, where they take little elements and they smash them together and make a new big one. They're radioactive. None of them are stable, and most of them only hang around for a few nanoseconds. So to me, they're a little pointless. Now, when they made the Hadron Collider in Switzerland, there were scientists who thought it was going to cause spontaneous black holes, microscopic black holes, and like people would start disappearing. And they turned it on anyway, and it melted down. But then it took them about 3 years, and they've got back up and running, and so far things aren't disappearing. So hopefully the whole black hole thing was not true. So have y'all heard about this? Do y'all follow science news at all? So they got one, I think it was last week or the week before, they smashed together one of the fake elements, and they got it to stay for like 2 minutes. It was big news because 2 minutes was enough to actually see some of its properties. I think it's a big waste of money, but you know, I'm not in charge, so they can keep doing this despite my low opinion of these experiments. Okay. Most elements are stable. Most of the elements on the periodic table are stable. Most elements are not radioactive. Does that make sense to you? Okay, and it depends on the ratio of protons to neutrons to whether or not it's radioactive or not. You see my radioactive rock? And here's a little graph that sort of shows you that this little red line is the band of stability. Protons on the bottom, neutrons on top. So like if you had 20 protons, you go look over at the periodic table and you see that's calcium. Then if calcium has just a little over 20 neutrons, it's stable and not radioactive. If it has a lot more radiation, more neutrons than that, it's going to have a kind of radiation called beta radiation. If it's, if you're over here, it gives off alpha. And this can give off or capture electrons. So these are just some different things, different kinds of radiation that are given off. And this is really simplified. All of this you'll learn a lot more about if you go further into this. And this is a part of science that is claimed by physics and chemistry. So usually you learn it in both classes. And we're going to go into it a little bit. But next year when you're in physics, you're going to go a lot more into this. So we're just giving you a taste of it. Okay, so all elements over number 83 are unstable and give off or eject radiation. So there was a question on the physical science exit exam, the end of course exam, that said, what isotope of uranium is stable? And none of them was not an answer. And I was like, I think they got something wrong with that test. But anyway, so if you learned that, If you took physical science, unlearn that. I'm giving you permission. Because all elements over 83, all of their isotopes are unstable and give off radiation. And remember, big E is energy. They give off particles and energy from the nucleus. Now then, the unit of radiation is named after the most famous woman scientist. So what is it? The curium, yes. Well, it's not, it's just the Curie. Curium is her element. It's the Curie, Marie Curie, Madame Curie. Is the most famous. So she, and you know, I think she died of radiation poisoning. So there you go. She's honored by. No, that was her husband. Her husband got hit by a horse. She died of radiation poisoning. She lived a long time after him. Did lots of experiments with radiation that she didn't realize was so harmful. Okay, so here are some types of radiation. The first one we're going to talk about is the alpha particle. It's really a helium atom. It has a positive charge. Skin blocks it. The symbol is this little fish-looking thing. That's the Greek letter alpha. And you can also have the symbol for it like this. This is the atomic number. And that is the atomic mass. And then, of course, that's the symbol. Also, they'll do it like this. And they'll put the little alpha particle symbol where the HE would go. How do we feel about that? Isn't that fun that you're learning something brand new that you've never learned before? Something kind of interesting. The next kind is called beta particles. Oh, let me tell you something about alpha particles. One time in college, I was working as a lab teacher, and at my lab, we were doing something with alpha particles, and they came in these little cylinders about this big. I would inject it with something to make it start being radioactive, to start it up. And then the students did experiments with the radiation. I bet they don't do that nowadays, don't you? Well, at the end, they were cleaning up, and they were bringing me their leftover supplies, and I held out my hand to take it, and I had said to them over and over again, make sure they stay upright. Don't spill your radiation. Keep it upright. This guy walks up to me and turns it over and puts it in my hand. It goes all over my arm, and I could feel it. It was very hot, which was weird because it was room temperature on the outside of the thing, but when it went all over me, it was real hot. But I didn't get superpowers. Lab accident, radiation, covered in radiation, no superpowers. I feel, what? What? Say it louder. What did you do to him? I told the teacher, I think he failed the lab for failing to follow instructions. But it's like, why would you do that? Like over and over. This is dangerous. Be careful. Don't spill it. And he just turns over and dumps it on me. But anyway, so, but luckily, look, your skin blocks it. So at least it was the safest of all the kinds of radiation. It was the safest one that I got spilt on me. Beta particles are really an electron. It's really an electron. It has a negative charge, and its symbol is this Greek letter beta, this B. And it's also sometimes written like this, a little e for electron, and this is where the mass number goes. And remember, electrons don't really have a mass, so instead of writing the mass, they write the charge to make the math work when we balance these equations. And you can see the mass up here is 0. Sometimes they'll write it like this with the B, and sometimes this B is not closed. Do you see how I wrote mine with a little gap? Don't let that fool you. Sometimes, I guess it's like different fonts of letters, because sometimes that is not closed. All right, don't you feel clever writing Greek letters? Doing a little Greek right here early in the morning. There's my little thing. There's the button. Okay, I'm going up. So the next one is gamma rays, and of course this is what turns Bruce Banner into the Hulk. Gamma rays. Let's see if I can get to go higher. Come on down. Oops, too high. Should have left. I guess I'll leave it there. Okay, gamma rays are really electromagnetic radiation. It's energy like light. remember we learned, what is this? Ronald, do you remember it? Ronald McDonald is very ugly, extra gross. Remember that was in your notes last time? Ronald McDonald is very ugly, extra gross. So this is the gross of Ronald McDonald is very ugly, extra gross. It's all forms of light. It all is given off by the sun and other stars. It all travels at the speed of light in a vacuum. So it's a type of light. It has no charge. It's only stopped by lead or several meters of concrete, and this is the stuff that's really going to give you cancer. This is the stuff that you don't want getting out of the nuclear power plant. This is the stuff that maybe would give you superpowers like the Hulk. I think the Hulk is like the worst of all the superheroes, that I would not want to become him. You used to love him? I used to love him too. I used to watch his TV show back when it was in the 70s when I was a little kid. It was always sad, though. It was always sad. It always ended with sad music. Okay, the symbol looks like that. Or sometimes they'll put zeros and then the little horns to make it look like that. Now, sometimes there can also be neutrons given off. It's called a neutrino. It's sort of like giving off a proton. The symbol is lowercase n, and then it's also written like this sometimes, where it has no protons, it has a mass of 1, and it's lowercase n. Remember when I was real picky about upper and lowercase with the elements, that nitrogen had to be capital N? Now you see why. Lowercase n is something else. It's a neutron. Now, neutrons have a secret. If you smack them hard enough, they'll split into a proton and an electron. And that's why neutrons are neutral, because they can become a proton and an electron, and a plus and a minus cancel each other out. Okay, and we're going to talk about that in a minute also. There's also a bunch of more things. There's quarks and mesons and gluons and all these extra particles you're going to learn more about in physics. But we're going to learn about just one other one called a positron. It's like a positive electron. And we really see it in fusion. So its symbol is, instead of just being a little e, it's a plus e, or it's a plus 0 on top, a plus on bottom, and an e. How do we feel about that? Do y'all want me to turn off the lights so it shines up better? Is that better?
Yes.
Yes. Sorry, I didn't think of that. Okay, so we're going to learn how to balance these equations. And to do that, we got to follow the law, and that's why we got a policeman there. He looks a little like, who's the policeman in Batman? Commissioner Gordon. That's who I was going for. All right. Because we had the Hulk, we needed Commissioner Gordon. But that's Marvel and DC. We're mixing comic books here. Okay, whoop, go back up.
Yeah, right there.
Like there? Okay. I took my finger off and it changed it. We'll try that. How about that? Okay. So the first law is the law of conservation of mass and energy. Mass and energy cannot be created or destroyed, just change forms from one to another. What you put in is what you get out. That's right. What you put in is what you get out. You can't make matter. So this is why in math you can't divide by 0. What happens if you try to divide by 0 in math? What does your calculator say? Error. And the reason why is you cannot divide by 0. Imagine I had a cake and I told you to cut it into 0 pieces. You can't. Even if you didn't cut it, it would be 1 piece. To make it 0 pieces, the atoms themselves would have to go away. And we can't make atoms go away. All we can do is change them from one form to another. Does that make a little bit of sense? So this is our first thing. We have to obey the law of conservation. The second one is the law of multiple proportions. In compounds, the subscripts are whole numbers. They are whole numbers, not fractions. I'm going to try to make it go up. Not that far. Come on back. Back it on up. Back it on up. Oops, too far. How about right there? Can we go there?
Yeah.
All right. So what is the formula for water? H2O. So water is H2O. It's not H2.25O3.75. No. Never decimals, always whole numbers. The next one is the law of definite proportions. The formula for compounds don't change. Water is always H2O, not H2O2. That's something else. Does anybody know what H2O2 is? It's peroxide, hydrogen peroxide. And when you buy hydrogen peroxide at the drugstore, it's only 3%. You can swish your mouth with it, you won't die. 30% is what people use to dye their hair, to strip all the color out of their hair. If you've heard of a peroxide blonde, they've used peroxide to strip their hair. And if you drank that, you would die. So 100% you cannot substitute for water. They are not the same. Any questions, Jeremiah? You getting it? All right. Nature likes balance. Nuclear equations must be balanced. So we're going to learn how to do this. But then we're going to kind of leave this alone. This little nuclear part we're doing is not what we normally do in chemistry class. Why not? What is this used for? What do they use nuclear chemistry for? Bombs. It's also used in treating cancer, but it can also give you cancer. So we're not going to mess with this. Our labs are going to be things like pennies and dominoes and Skittles. We're not going to use alpha particles. So we're going to do this, and then we're going to kind of move on. And we're going to move to real equations, chemical equations. And they'll work similar to this, but we'll be moving off of this pretty quickly. All right, so there's our balance. All right, next page. In a chemical reaction, reactants are written over here, then an arrow, then the products. Okay, so reactants, the arrow sort of like is what it yields, what it makes, but you can sort of think of it as an equal sign. Okay, it must be equal on each side of the arrow. So these are the rules of how we're going to do this. Now there are two kinds. There's splitting an atom. What's it called? Here's your hint. Fission, right? Fission is splitting the atom. And it's like if you have, it can be a bomb if you have enough stuff. Now, if you don't have enough stuff, it won't make a bomb. And enough stuff, that's not very sciencey sounding. Enough stuff is called the critical mass. That sounds much more sciencey, doesn't it? Critical mass. And it will start a chain reaction. And we're going to do a lab with that with dominoes. Okay? Also, this is the kind of nuclear chemistry that's used in our nuclear power plants. Now, that's been in the news lately, too. What happened with the nuclear power plant that made the news this week? That was my hint. I was showing you respect. What country do you show respect like that? Japan, right? In Japan, they had a nuclear power plant. They had an earthquake. It busted it. It was leaking radiation all over the place, all the way into the Pacific Ocean. California's getting the radiation. Washington State now. They kind of got it calmed down a little bit, not completely. And they had another earthquake last week, and the numbers are spiking again. So, just my personal opinion, I don't think they're a good idea. I think we can find power other ways without something that dangerous.
I mean, how many times has nuclear power plants exploded?
Chernobyl, 3 Mile Island, wasn't that one?
Yeah.
This one, it's not, the thing is I think we think we can control this, and it's just too big. We can't control it. So I don't think we should try. But maybe one day, but we're not there yet because, I mean, it was bad. You know,
You'd think they'd be smart and be like, hey, let's stop doing this.
I think scientists are arrogant. I think a lot of times they do things and they don't think whether or not they could do it, whether or not they should do it. Does that make sense? I think that these are people who have been told they were brilliant since they were babies. And they get a little prideful, I think, and get too big for their britches. So that's just my personal commentary. Now, if your parent is a nuclear scientist working on nuclear power, they might have a different opinion. I actually had that once. One of my students in Cobb County, his dad was a nuclear chemist, and he worked at a power plant. And he came, and I got him to come speak to my class, and nobody except me understood a word he said. He was talking so above the kids' heads. I'm like, why do you think they understand you? You know, I have a degree in biochem. I can understand you, but nobody, all my students were very polite and listened to him, but oh my goodness, he was so smart.
You just gotta nod your head and let them keep
Yes.
keep talking.
That's what they did. They were. I thought they are so sweet to just be polite to him, but I mean, he was crazy over their heads. All right, it's used in nuclear power plants. The other one is where you put atoms together, and this is our hand signal for it. So this is fission. This one is fusion. Putting atoms together, like in the sun, that's why we got the sun here, and all the other stars, it gives off energy because E equals what? What does E equal?
MC squared.
MC squared, that's right. And this mass is being converted to energy in it, but not gotten rid of. You can't get rid of it. So now we're going to learn how to balance nuclear equations. Doesn't that sound fun? You're going to learn something new. All right, so this is our first one. It's our neutron. And what was the symbol? What number needs to go down here at the bottom of the neutron? A 0, because it has no protons, right? So y'all can write it littler and make it look good. My pen's too fat. What's the number for protons? If you have one proton, how many protons does it have? It's got 1, right? So we put a 1 there. And electrons, we do -1. So a neutron is made out of a proton and an electron. Okay, how do we feel about that? Okay, now this is the part you got to pay close attention to. This is the key of how to do it. Yes? Go what? Go down. You want to see what's up there? Yes. Now find the button. Button. Where is the button? Okay. I'm going to give y'all a chance to write because I want y'all to really pay attention here because this is the key to you being able to do all these problems. They're pretty easy.
Wait, so like go over the first one again?
I will. But I'm going to give people a chance to write for a second. When you do this on the test, I want you to use your calculator. Because if you get it wrong, I want it to be because you didn't understand the chemistry, not because you had a brain malfunction and forgot that 2 + 3 is 5. And that happens. Sometimes on a test, your brain will just kind of jump around. So have your calculator and double check your numbers with your calculator, okay? When we do this test. All right. Let's go over it again. So the arrow is an equals, and the numbers have to equal on both sides. So if we look at the bottom, 1 minus 1 is 0. And if we look at the top, 1 plus 0 is 1. Do you see how those are equal? Okay. 1 minus 1 is 0, and 1 plus 0 is 1. Do you see how the numbers work out? Okay, let's try another one. I'll do it with you. Get this where I can just leave it alone now. Get it back up. it back. Right there. All right. So with this one, look at your periodic table. Everybody get out your periodic table that I gave you a copy of, or if you want to, you can look over there. But you're going to have to use a periodic table to get all the numbers. What is the atomic number of americium? Americium. Looks like Americanium. What's its atomic number? How much? 95. So we are going to look that up and write it right there. What is the atomic number of neptunium? 93. Does everybody understand how she's doing that? Look for the whole number, not the decimal. And then, what is the atomic number of helium? 2. Now we're going to check the math. Is 93 plus 2 95? Yes. Is 237 plus 4 241? Do you see how the top and bottom are equal to each other? I see nods. Good. Hope, put away your phone. Thank you. No phones, unless you're taking my picture. All right, let's try the next one. Try the next one. Look up what is the atomic number of iodine. What's iodine? 53. What is the atomic number of xenon? 54. What is the symbol that goes on the bottom for the beta particle? What number goes there? Negative 1. Does the math work? 51 minus 1 is 53. 131 plus 0 is 131. We're starting to understand it a little bit? Good. Try the next, no, we'll do the next one together. Okay, so what is the atomic number for radon? You see it? It's over there near francium. 88. 88. And what is the radium? What is the atomic number of radon? There it is. It is 86. What's the atomic number for helium? 2. And what do you put on a gamma ray on the bottom? 0. Let's check the math. Is 86 plus 2 plus 0 88?
Yes.
Is 222 plus 4 plus 0 226?
Yes.
Yes, okay. So let's do, try the next one all by yourself. See if you can figure out how to do the next line by yourself. Look up the mass of the number of cobalt and nickel, beta particle and gamma particle. See if you can get it. Did you get them? 27, 28, negative 1, 0. Okay, now we're going to do one that's much more like what they'll be like on the test. Okay, so let's do this one together. What is the atomic number for uranium? 92. Oh, whenever I hear uranium, I want to be plankton and go, bombs. Do y'all know what I'm talking about? F is for friends who do stuff together. U is for you and me. Right? Yeah, does anybody know all the words to the friendship song from SpongeBob?
I don't know what N is.
You don't know any of the words to the friendship song from SpongeBob? Well, maybe somebody else will sing it to you. Okay, what is the atomic number for thorium? TH, what's it?
90.
90. So now we need to figure out what's the missing thing. What do we need right here? What do you add to 90 to get 92? 2. Which is what? Emily said it? Didn't you say it? Helium. Oh, sorry. There we go. Who was it? Oh, it was Hope. Hope got it. So it's helium. Don't let that 28 confuse you. So now let's see if it works. 233 is 229 plus 4 233? Yes, it is. I know that's kind of confusing because the 28 is right on top of that. Okay, I want y'all to try the next one by yourself. Try them and see if you can do the next one by yourself. See my bomb? Doesn't that look good?
That's a bomb.
Mm-hmm. That's a nuclear bomb going off because it makes that little ring around it. You thought it was a tree with a ring around it? Nope, it's a bomb. Okay. Okay, did you get it? What's the number for Neptunium?
93.
93. What's the number for Plutonium? 94. So what is our missing thing? It's the beta particle, right? 0, -1, E. Because 94 minus 1 is 93. And 239 plus 0 is 239. Do you like this math? It's not terrible, is it?
Yeah.
Try the next one by yourself. Try the next one by yourself. See if you can figure it out. Oh, that's not a bad negative one. What minus 1 is 29? In math, what minus 1 is 29? 30. What is element number 30? Zinc. And what is 66? What plus 0 is 66? What do you add to 0 to get 66? 66. Does that one make sense? How do you feel about it? A little bit? I'm seeing less frowns, so that's good. Okay, try the next one by yourself. See if you can get it, and then you can look up here and see if you got it right. Did you get it? What's beryllium's number? 4. What's carbon's number?
6.
What do you add to beryllium to get 6? 2, a helium. Some people are getting this really good. Okay, let's try the next one. What is carbon's number? 6, so we can fill those in. What will we add to 6 to get 6? What plus nothing, so that's a 0. And what do we add to 12 to get 13? So what is our missing symbol here? What are we missing? Nope.
Positron.
No, because of the mass. We had to have a mass of 1, and positrons have no mass. So it's the neutrino, it's the neutron. It's the neutron is what we had to add to it.
Does it matter?
Either one, you can call it either one. It's got 2 names. Okay, and now this is our one, this is phosphorus. So what's the atomic number for phosphorus? 15. Neutrons are 0. What's 15 plus 0? 15. So what is it? It's 15, which is a phosphorus. And now what's 32 plus 1? 33. 33. Okay, so we're going to be able to do those on the test, no problem?
Yeah.
Good. Let's find the button. There's the button. Did everybody get those, or do I need to go back to it? I think I gotta go back.
I think we skipped something.
I think so too. That's where I'm trying to get to. Half-life. All right. So these isotopes, they turn into something else. You saw it on the equations. You started with copper, you ended up with zinc. You start with uranium, you ended up with helium and thorium. Do you see that? So half-life is the time it takes for half 1/2 of the sample to turn into something else. It is the time it takes for half of the sample to turn into something else. For example, carbon-14 decays, I said to carbon-12. It really decays to nitrogen. But so we'll work on that. But anyway, carbon's half-life is 5,715 years. Just know that it's half-life. It decays. We won't say what it decays to. Just say it decays. Carbon-14 decays in 5,715 years. And when it does, it emits the beta particles. So this is used, you are a carbon-based life form. This is to date things like bones. If they find some old bones, they look to see how much carbon-14's in it. They figure out how old the bone is. Now, like back in the dark ages of when I was your age, we thought as scientists that this was foolproof. We thought we could set clocks with it and have atomic clocks, and it was perfect. But that was a long time ago, as y'all can deduce. And now they're starting to think that maybe we made assumptions. And whenever you make assumptions, you open yourself to error. The assumption was that the levels of carbon-14 now are what they always used to be. I don't know if that was the problem. But then they started getting problems in the 90s, when I first started teaching, about where like living monkeys would be dated tens of thousands of years old. So they started realizing there were problems with it. Another thing was there would be a sample that was supposedly so old it should have no carbon-14 in it at all, but instead it would have some, and they would say it was contamination. But now we've gotten to the point with lasers that we can make sure there is not one atom in the machine that shouldn't be there, and there's still carbon-14. So now they're starting to say, and this is just within the last 5 years, that we don't know everything about this. Surprising? No. Things that either this is not as steady as they thought it was, or things are not as old as we thought it was. Instead of millions of years, maybe hundreds of thousands, or maybe tens of thousands of years. That things might not be as old. Maybe that's why there's carbon-14. Maybe it's not as steady as we thought it was. But this should not discourage you. You can all know that we haven't discovered everything. There's room for you to be a scientist and grow up and discover something. You might be the person to figure this all out. Some of y'all are thinking, nah. But maybe, right? Caitlin, put your phone away. Unless you're taking my picture. No phones. No phones. You got to pay attention. This is hard. We want better grades. Y'all's grades have been okay. But y'all are not performing at the level I want you to. I want way more A's and no F's. We've been getting less A's than I'm shooting for and more F's than I'm shooting for. So we need more paying attention. And for a few of you, I might be changing your seat too. Some of you need to come closer to my magnetic personality. So don't be surprised if there'll be a new seating chart coming, because some of y'all, I want to get a little closer to me so I can see in your eyes if you're understanding. So if you don't want to be close to me, do really good. And I might let you be not quite as close. All right. But some of y'all need more of me in your life, more of my wonderful personality. All right. So here's an example. I can get to do what I want. Yeah, I want to go a little bit too far. Up a little. Yeah, we're just going to go with that. All right. So here's an example of carbon-14 decaying. So what number is carbon? What's its atomic number? 6. And what is the sign that we put with the beta particle? -1. So what's missing here? What minus 1 is 6? 7. What element is 7? Nitrogen. What plus 0 is 14? 14. So carbon 14 is going to turn into nitrogen 14. Now we're going to make a graph of this. So this is the big thing you always do with half-lives. You got to make the graph. So whoop, go back up. Go back down. Come on, we can get it right. No, we can't. Ooh, that was pretty close. Ah. Come on, just a little bit. Just a little bit. Give me the graph. That'll work. Okay. So when you start off at 0 years, you've got your sample. You have 100% of your sample has got carbon 14. None of it's decayed yet. So we can graph it. At 0 years, we have 100%. Put a dot there. After the half-life of carbon, 5,715 years theoretically, half of it would turn into something else. One half-life would go by, and you put a dot at 50%. In another 5,715 years, now it's 11,430 years have passed since we started, then half of this will go away. So what's half of 50%? 25%. So we go to 2 half-lives, and at 25 we put a dot. Now let's go to how much would be left after 3 half-lives? 12.5, yes. He is getting it. So we go half of the half and put a dot. What is half of 12.5? That's a tricky one. 6.25. So we go to 4 half-lives, go half of the distance, and put a dot. What is half of 6.25? 3.125. So we can go on out here, make our 5th half-life, go half the distance, and put a dot. And then 6 would be 1.5625. So you go half again and put a dot. Connect your dots, and this is what a half-life graph looks like. Classic shape of a half-life graph. Okay, some isotopes have more or less neutrons. That's what makes them isotopes. Like a fat cat or a skinny cat. These are my cats. This is Tigger and Ruby. Ruby's fat, Tigger's skinny. And they both have the same amount of food. He exercises more. He runs around like a mad cat. She just sort of sits around, gives you emotional support. They were Tigger and Roo, and then she became Ruby, because they were like Winnie the Pooh. Okay, they're both rescue cats, taken from outside. Okay, they have the same number of protons. Protons is what make it what it is. Protons. Some isotopes have special names. In particular, these of hydrogen. In fact, this is protium, and all it is 1 proton. Deuterium has a proton and a neutron. And tritium has 2 neutrons and 1 proton. So that's tritium. And you might do some lab stuff with that when you're in college. We don't really worry about that in high school. You won't be doing anything with isotopes because, once again, we don't do anything too dangerous. We don't work with the radioactive stuff. We try not to work with anything that will give you cancer. Now, why are the mass numbers on the periodic table a decimal? It's because it is a weighted average, like grades. You can't take all your grades, add them up, and divide by how many you have. Why not? Are they all worth the same thing? No. Summative is worth more than formative, isn't it? End of course is worth more than everything. Until this year with COVID, they made it not worth so much. Did y'all follow all of that in the news when they made your EOCs not worth anything? We don't have one in here. So you'll have a final that will be worth something. All right, we are going to stop here and we're going to do a lab. We got 30 minutes. That's about how long the lab will take. And so what I want y'all to do is I want you to, when I tell you to, I want you to put up your markers and I want you to go sit with your lab partner and I want you to find another partnership you can work with. I want groups of 4 or 5 kids per group. So you and your partner find another group and y'all all go sit together. Science is great. Come back for part 2.